welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and today we're going to be doing Unit 9, Lesson number 6, Motion in Two Dimensions. So this is a great follow-up to our last lesson where we looked at the calculus of parametrically defined functions. Now what we're going to be doing is looking at motion in two dimensions, and this really puts it all together. Let's jump right into it. All right, exercise number 1, kind of crowded on the sheet, but I hope we can move my head around enough so that you can see everything. Tells us that we have a particle moving in the xy plane, so two-dimensional motion, a particle moving in the xy plane from point A to point C, or to point B to point C, as shown below. Its position is given by these two parametric equations, where x and y are measured in meters and time is measured in seconds. The object's path in the xy plane is shown below. Letter A asks us to write an expression for the velocity vector at t equals 0. Well, we know in one-dimensional motion that the velocity is the derivative of position. That's going to be exactly the case here too, except now the velocity vector, is going to be the derivative 2t minus 7 and 5 minus 3 divided by t plus 1. Right? If we take the derivative of both the x-coordinate and the y-coordinate, and then we evaluate it at t equals 0, we'll have our velocity vector, which would be negative 7, 2. By the way, take a look at that for a second. You can almost think about that as being sort of the direction vector, right? Because we know velocity controls direction. And if we let me actually put it in a different color. If we put it in red down here, and we just draw like a little vector coming off the top, it seems pretty obvious that, yeah, it's heading to the left and it's heading up, which is exactly what that vector would suggest. Now, letter B is pretty easy, right? Find the speed of the car at t equals 0. I'm not sure why it suddenly became a car, but it did. Now, what we know is in one dimension, speed is the absolute value in velocity. In 2D, it continues to be that way. Speed is the size of the velocity vector, right? So we'll take the square root, we'll get 49 and 4, not the prettiest thing though, and we'll have the square root of 53. Now, speed will always have the same units as velocity, so we have the square root of 53 meters per second. Letter C, determine an expression for the acceleration vector at t equals 0. Well, we know the acceleration is the derivative of velocity, and it continues to be that way. In fact, we can actually write down very formally that the acceleration vector will be the derivative of the velocity vector. And let's kind of do this in general, all right? So, and then we'll evaluate it at t equals 0. If I take the derivative of the x component of velocity, we'll get a nice constant, which is 2. Now, the derivative of the y component is a little bit trickier, but that would be 3 divided by t plus 1 quantity squared. So if we use the power rule or the quotient rule or something like that, now specifically at t equals 0, that ends up just being the vector 2, 3. Very simple. Letter D. At point B, the particle changes from moving left to moving right. That's pretty obvious, right? We're heading left up to point B, and then we're heading right after point B. It asks us at what time t does this occur? Justify. Pause the video for a moment, think about that if you need to, and then let's come up with when that occurs. All right. Well, it's all about moving left and right. And the real key here is that all that really has to do is with the velocity in the x direction, right? Here's dx dt. Way down here at the bottom of the screen, I apologize, dx dt is 2t minus 7. If I set that equal to 0, I find that t is 3.5, or 7 halves. Now I'd want to really kind of make sure of what was going on here, so if I put, let's say, 3.5, let's label this as my velocity. Maybe you subscript it with an x, right? It's the velocity in the x direction. Maybe throw in a starting time of 0. If I take, let's say, a time t equals 1 and I substitute it in here, I'll find a negative velocity, which means I'm moving to the left. If I take a number like 4 and I substitute it in here, I'll find a positive velocity, meaning I'm moving to the right. It doesn't tell us anything at all about our vertical motion, but it does tell us that our horizontal motion changes direction there. So we can justify this by saying changes direction because maybe v with a subscript x changes sign. All right, pretty easy. So what we always want to do throughout this entire lesson, as much as possible, is extend concepts about one-dimensional motion to 2 dimensions. All right, I'm going to clear out all this crazy text, so copy down anything you need to. All right, here it goes. All right, let's move on to the next problem. See what we can do. Well, actually, let's just summarize it. So it's pretty easy, right? In one-dimensional motion, we had position, we had velocity, we had acceleration, we had speed. We still have all of those, except position, velocity, and acceleration are now all vectors. And it's simple enough, right? The position vector is just literally the x-coordinate, comma, y-coordinate. The velocity vector is the derivative of the x-coordinate, comma, the derivative of the y-coordinate. And the acceleration vector are the second derivatives, or the derivatives of the velocities, but it's kind of harder to write that in this notation. The speed is just the length, or the magnitude, of the velocity vector, right? So if we find the length of this vector, we would do it using the speed. Or do it using that formula. Let me clear that out. Now let's move on to the next problem. All right, an object moves around a circle of radius 8 inches such that its position is given by those two position formulas, where the position is in inches, right, and time is in minutes. And the first thing it says, or the first thing it asks, is for us to show that the speed of this object is constant, and also to find the speed and include units in my answer. Ooh, show that the speed is constant. What I'd like you to do is pause the video right now and work for maybe upwards of 10 minutes to see if you can do that, to show that the speed is constant and to find the speed and include units in the answer. All right, let's pause the video for a bit. All right, let's do it. Well, if they say show the speed's constant, the best thing to do is just try to find the speed, right? The speed is the length or the magnitude of the velocity vector. So what I'm going to do is I'm going to find the x component of velocity by taking the derivative, right? What will that be? That will be negative 16 times the sine of 2t. The y component of the velocity, y prime of t, that's going to be positive 16 times the cosine of 2t. So we can actually write an equation for the speed, right? Actually, let me write it up here. That'll give us a little bit more room. Write it right here, right? The speed is going to be the square root, oh, look at that, of the x-coordinate, negative 16 times sine 2t squared plus 16 times the cosine of 2t squared. Let's keep going with that. Well, 16 squared is 256 times sine squared 2t plus 256 times cosine squared 2t. Let's extend that a little bit farther. I think I'll factor that 256 out because that seems common to both. And then I'll have sine squared 2t plus cosine squared 2t. But this is the Pythagorean identity, and it's equal to 1, right? So the speed is, in fact, just the square root of 256, which is 16. That's my speed. And it's going to be in inches per minute. So, in fact, I kind of accomplish everything in one fell swoop, right? Not only do we prove that the speed is constant, but we find out what that constant is, 16 inches per minute, and we come up with its units. All right. Letter B says, find an expression for the acceleration vector of the object for any time t. What angle does the acceleration vector make with the velocity vector for any time t? Whoa. Okay, let's just take it a little piece at a time. First thing I want is an expression for the acceleration vector. Now, we know that is going to be the derivative of the velocity vector. So I need to find the derivative of the x-coordinate of the velocity I need to find the derivative of the y-coordinate of the velocity. Why don't we put it down here? All right, let's see. Here's my x component of the velocity. So if I take its derivative, what I'll have is I'll have negative 32 times the cosine of 2t, right? And then if I take the derivative of the y component, that will be negative 32 times the sine of 2t. All right. Well, there it is. That accomplishes the first thing the problem asks me to do. There is an expression for the acceleration of the object for any time t. Now it asks, what angle does the acceleration vector make with the velocity vector? The only thing that allowed me to find angles so far when it comes to vectors is the dot product. Let me do that in red. The dot product. All right. So let's do this. Let's find up here, let's find A dot V. All right, now we have A, and up here we actually have V, so let me write that out formally. The velocity vector is negative 16 times the sine of 2t and 16 cosine of 2t. So let's dot A with V. You know how to do the dot product, right? It would be negative 16 sine 2t, that's the x component of the velocity, times the x component of the acceleration, plus now the y component of the velocity, times the y component of the acceleration. Oh, I'm running out of room. Well, it's not the prettiest thing on earth, but this is going to give me, I'm going to look at my numbers here, 516 times sine 2t cosine 2t minus 516 times the sine of 2t times the cosine of 2t. Well, that's 0. So A dot V is 0. Pause the video for a second and think about what that means. Okay, this is where your dot product work pays off. The dot product of two vectors will only be 0 if A and V make a 90-degree angle with each other. All right, so A and V are perpendicular. This takes us back to physics. If you've had some introductory physics, one thing that you might have studied was what's called uniform circular motion. That's an object going around a circle at a constant speed. That's what we saw in letter A, right? I mean, the thing had a constant speed. And one thing that they like to prove, or at least teach in introductory physics, is that when you have an object going around in uniform circular motion, the acceleration and the velocity are always perpendicular to one another, which is kind of cool. All right, well, I'm going to clear out this text, so copy down anything you need to. Okay, here it goes. Gone. All right, let's take a look at number 3. It says, given that the speed of an object is s equals dx dt squared plus dy dt squared under the square root, develop a criteria to determine whether the speed is increasing and when it is decreasing. So back in one-dimensional motion, what we saw was that the speed increased when the velocity and acceleration had the same sign, and it decreased when they had opposite signs. Velocity and acceleration are now vectors, so we can't compare their signs. So we're going to go at it straightforward. We're going to find the derivative of the speed, and we're going to figure out when it's positive and when it's negative. And the result, in my mind, is really, really cool. So let's do it. Now, I'm going to rewrite this as, I think rewrite it as x prime of t squared plus y prime of t squared to the 1/2. So let's figure out ds dt. Okay, I'm going to do that using the chain rule. I'm going to bring that 1/2 down. X prime of t squared, lots of parentheses here, my apologies. Y prime of t squared to the negative 1/2 times now the derivative of what's inside. What's the derivative of what's inside? Let's see, it would be 2, so we have to do this using the chain rule as well. 2 times x prime times x double prime plus 2 times y prime times, whoops, that didn't look good, times y double prime. There we go. I'm going to clean this up a bit. I'm going to take this 1/2, I'm going to cancel all these, and I'm going to rewrite it like this. X prime of t times x double prime of t, it's a double prime, plus y prime of t times y double prime of t, all divided by the square root of x prime squared plus y prime squared. All right, so there's the derivative of our speed function. Now, we know how derivatives work, right? If the derivative is positive, that speed function will increase. If the derivative is negative, it will decrease. And yet, still, I want something nicer. So what I'd like you to do is I'd like you to take a look at this. Hopefully, you'll all agree with me that the denominator is a positive number. It's a positive square root, so it's a positive number. But the numerator actually looks like something familiar. I got the x component of the velocity times the x component of the acceleration, right? X component of velocity, x component of acceleration. In fact, maybe I'll just do that. Vx times ax plus Vy times Ay all over, honestly, that the bottom is the speed. But that means that the top is the dot product. Do you see that? That's just V dot A divided by the speed. Now this is really kind of cool, right? Because what this says is that ds dt will be greater than 0 if V dot A is greater than 0, right? And the speed will increase. Lots of work today on the intercom and the bell systems. The derivative of speed will be less than 0 if V dot A is less than 0. Now, this should make sense, right? Think about this for a minute. The dot product is all about alignment. So by saying that the dot product of the velocity and acceleration is greater than 0, just means that the velocity and the acceleration are either working completely together or somewhat together. You know, they're not opposite of each other. Likewise, if the dot product of the velocity and acceleration is less than 0, then the speed must be decreasing. So it's all about the alignment, whether velocity and acceleration are working together or they're working opposite of each other, or at least somewhat opposite of each other. So that's the criterion, all about the dot product of velocity and acceleration. Isn't that kind of neat? I love that as an extension of the one-dimensional case. I'm going to clear it. It's gone. Let's do one application of that, and then we'll be done. Exercise 4. An object moves along an elliptical path such that its position, as a function of time in seconds, is given by that position vector. And then it asks us if the speed of the object is increasing or decreasing at t equals 5 seconds. Justify. All right. Be kind of ugly, and I need my calculator on it. But let's figure out our velocity vector, right? If I take the derivative, I'll get negative 5 times the sine of t, and 2 times the cosine of t. And the acceleration vector would be negative 5 times the cosine of t, and negative 2 times the sine of t. Now, obviously, t equals 5 is not particularly a nice time or angle or whatever you want to think about it as. So maybe I'll just write it as negative 5 times the sine of 5 and 2 times the cosine of 5. And this is obviously negative 5 times the cosine of 5 and negative 2 times the sine of 5. We could work all those out in terms of messy decimals, but ultimately we just need to know what a times v is. So we could, kind of simplify it a little bit and get 25 times the sine of 5 cosine of 5 minus 4 times the sine of 5 cosine of 5. If we really wanted to take this to the extreme, we could say that that was 21 times the sine of 5 times the cosine of 5. And then eventually work it out. That is in its ugly decimal form, negative 5.17. Whoops, nope, made a little mistake there. Sorry about that. 5.712. And because that dot product is negative, right, what that tells us is that A and V must be at obtuse angles to each other. Again, I don't know what the angle is, although we do have the ability to find it. And because of that, speed is decreasing. Isn't that amazing? Right. So without graphing the path, without knowing much about it at all, I can tell whether the object is speeding up or slowing down by using the dot product. It's kind of neat. All right. Well, I'm going to clear out the text, so copy down anything you need to. All right, here we go. Okay, well that was it. And that kind of ends our unit on parametric equations and on motion in 2 dimensions and the calculus of parametric functions. For the next couple lessons, we're going to get work on old AP type problems, and then we're going to start modeling a variety of different motion problems. So this will probably be the last video for a little while because it's the last really uniquely new lesson. For now, let me just say this has been another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler. And until next time, keep thinking, keep solving problems.